Hi, in Unit 4 we learned about the organometallics, and in this video I want to summarize the reactions of two of them, the Grignard reagent and the Gilman reagent. In particular, the Grignard reagent is extremely useful to make carbon-carbon bonds, and here on the screen I've drawn some molecules, some very important biologically active molecules, where a certain bond was made via a Grignard reaction. It's the bond in pink. Now, the idea for a reaction roadmap is to show how these reactions are all connected, or to show how one city can have many roads leading to and from it, going to other cities. In the middle, let's give a Grignard reagent. Let me give us this one here. And I'm going to draw a couple roads, a couple cities, and then we could practice filling in the blanks. Okay, as you see here, I have some reagents that are blank. I have some products that are blank that need to be filled in. Why don't you go ahead and copy this? So I'm showing everything that's given in black, and the next thing I want to do to practice is to categorize each of these molecules, because maybe it's a little bit easier if we verbalize what the reactants are. For instance, Grignard with a ketone should give us a certain type of alcohol, tertiary alcohol. Or we could say Grignard plus something gives us a secondary alcohol. Alright, so let me get started and you can finish the rest. I'll do this in green. This is the Grignard reagent. And this is a ketone. Okay. Don't worry about categorizing the molecules that are blank. We could do that afterwards, after we've decided what reagents to react. So it's your turn. Go ahead and categorize as many of these molecules as you can. You don't have to categorize the hydronium, which is the acid that protonates the alkoxide. Okay, I've categorized as many as I can right now. What is this arrow here going to the Grignard reagent? That's probably asking, how do we get to the city? How do we synthesize the Grignard reagent? And the best way to synthesize, well, the only way that we've learned how to synthesize a Grignard reagent is from an alkyl halide. Typically, the alkyl halide you want to use is an alkyl bromide. So there used to be bromine on this carbon right here. Just make sure you have the right number of carbons, and then you have this bromine. In the reaction, you react it with magnesium. Sometimes I like to put 0 to emphasize that it's the metal, the neutral atom, not the cation, not the 2+ magnesium. And many professors would like a solvent, a dry solvent, typically an aprotic solvent. Okay. All right. So that's the synthesis of a Grignard reagent. Next, we're going to react it with formaldehyde. Whenever you feel you can fill in the product, go ahead and pause the video. We're going to do this in blue. Okay. Let me show you how I would think about the addition of formaldehyde. You have carbon here that's partial positive off of the double bond oxygen, and this carbon is partial negative. But you are using the bond to make, using this bond to make a new connection between this partial negative carbon and this partial positive carbon. So I like to locate the carbon that I'm attacking and put a dot. So it's not that carbon is here. This carbon attacked, a dot. And in your Grignard reaction, your carbonyl group becomes a hydroxyl. Okay, we're putting together a roadmap. We're not showing the mechanism. But here we formed a primary alcohol. Primary because this carbon has no R group, but we added the R group of the Grignard. So what do you think happens if the resulting alcohol has two R groups? Well, here's one of them, and what color should I use now? Oh man, let's use red. So, let's use pink. So here's one, and if you think about it, your carbon-carbon bond that you made was this one. So your carbonyl has to have these 4 carbons. And it is an aldehyde. It has one group already. We added a second group to make the secondary alcohol. Alright, technically this is an aldehyde, but formally, or more specifically, is formaldehyde. It has 2 hydrogens. This one only has 1 off of the carbonyl. And please don't forget that you have to protonate, because after the initial attack, that's an O-. You need acid to put that proton there. Do you want to give this a shot? Go ahead and put the dot. And how would your alcohol in this case look like? Do you have this molecule here? Did you forget the OH? Remember, the carbonyl becomes a hydroxyl, and here we have our tertiary alcohol. Okay, so on the right side of the roadmap, pretty straightforward. The carbon you attack, and the carbon you attack, that double bond oxygen becomes a hydroxyl group. But here we have a dilemma, because this carbon right here, if we label this carbon number 1, okay, that carbon is actually right here. So the bond we made didn't attack a carbon which ended up with the OH. Do you see how every time we have this dot, right, that's where the OH is? Because we attacked a carbonyl group. But in this case, we attacked a carbon that was not a carbonyl group. There was something special about this molecule that we attacked. So we did attack this, but the hydroxyl group did not end up there, because we didn't attack a carbonyl, we attacked an epoxide. So how do we figure out the structure of this epoxide? Well, that O was initially connected to this carbon as well as a triangle. So visualize a triangle here. And I could draw it upside down, just the way I visualized it, the O over here. And then we have this group. Okay. If you want to number it, you could. We could call this carbon number 1 of the epoxide. That's this one here. 2, 2, 3, 4, 3, and 4. Okay, so there was an attack on this carbon, the less substituted carbon of the epoxide, and it broke this leg. And that's why the oxygen is still attached to carbon number 2, but not attached to carbon number 1. And again, we have to protonate. Okay. The next one, you may or may have not seen this, is carbon dioxide. Remember how I said that this carbon is partial negative? But all of these other carbons, the ones with the blue dots in the reagents, those are all partial positive. Well, we have a partial positive carbon right here as well. So that Grignard reagent is going to attack this carbon here. Even if you haven't seen this reaction, based on the mechanisms of these first 4, you should know what happens here. Because once that carbon gets attacked, you know you're going to make this carbonyl group an OH. The thing is, this carbonyl group, nothing happens to it. you just pick one of them to make the OH. Carefully draw your Grignard reagent. So there's the last carbon, that's carbon number 1. And it attacked CO2. There's your dot. That dot is this carbon. Let's say this oxygen stayed as a double bond. But when we attack this carbon, maybe this pi bond was the one that moved to the oxygen. So now it's a single bond. That used to be an O-, but then we protonated. So this is very interesting. We've been getting alcohols all along, even with the epoxide, but in this case, since we attacked a carbon that has 2 oxygens on it, we get this structure. This is a carboxylic acid. It's a very tricky way, very clever way to go from an alkyl halide that has how many carbons here? 1, 2, 3, 4, 5, 6 to a carboxylic acid with an extra carbon, C7. 1, 2, 3, 4, 5, 6, 7. That 7th carbon was this carbon from carbon dioxide. Okay, so that reaction, possibly new for some of you, could still be figured out with the knowledge that you've known or knowledge that you've gathered before. Now, if you're using this roadmap as an overview of all the organometallic or all the Grignard reactions in the semester, there's one more that you'll learn, or you have learned, and that's with an ester. Don't worry about the mechanism if you haven't gotten up to this yet. And honestly, don't worry about the product. This is really just for completeness, because by the end of the semester, you'll know what happens when you have a Grignard reagent react with an ester. So there's your ester, carbon. No, that's not the ester carbon. That carbon's carbon number 1. So you got to be very careful. You attack the ester carbon. There's the dot for that. What happens here is that this group stays, but this one leaves. And that carbonyl still becomes an OH. So the weird thing about Grignard plus ester is that you actually add the Grignard twice. So now I really got to be careful that I have the right number of carbons. And we made 2 bonds. We made this bond here, and then this bond here. Again, if you have not gotten up to this reaction yet, don't worry about it. But in whole, by the end of the semester, these are the reactions of the Grignard reagent. Now, before we take a look at the Gilman, okay, let me just say that whatever you can do with a Grignard, you could do with an organolithium. So let me draw a road to organolithium. Li, metal, aprotic solvent, and quite simply, you just replace the bromine with a lithium. And if you had that reagent in the here, all the same reactions will happen. Okay. Alright. Let's take a look at the Gilman. We're going to make a Gilman and then we are going to react it. Let me start with a simpler alkyl halide. Or maybe not simpler, but a different one. So to make the Gilman from an alkyl halide, do you remember? You first convert it to the organolithium. Another aprotic solvent that you could use is, you have diethyl ether there. Maybe hexane? Maybe hexane. And we get the organolithium. We need that already. But to make it into the Gilman reagent, we use copper iodide. Don't worry about the stoichiometry, but actually you need 2 of these for every 1 copper iodide, because you've learned that the Gilman reagent has a funny form. You definitely attach it to copper lithium now, not iodide, so there's an exchange, but there's two. So whatever you see here, you see 6 carbons, all 6 carbons have to be within those parentheses. There is one reaction that is very popular using the Gilman reagent, and that's adding another alkyl halide. So, and that alkyl halide, that bromide or chloride can be off of a sp2 carbon. And actually for the Grignard, that Mg, we could have made a Grignard coming off of this sp2 carbon as well, if the bromine was coming off of that carbon. Anyway, let me do that. And I'll use chloride. You could use bromide as well. The trick is that carbon, partial negative, will attack this carbon, partial positive. And you're only adding the Gilman group just once. So this is the dot. That's the carbon that's attacked. So I guess this is a dot. And then we have this. You don't have to worry about cis or trans. I would try to draw the trans, which is more stable than the cis. But I don't require my students to draw both. What we get is a hydrocarbon. There's no alcohol. So if you're making a more complicated or longer hydrocarbon, it's pretty easy to make that new carbon-carbon bond via a Gilman plus an alkyl halide. Give that a go. See if reactions are a little bit more easily recalled if you learn them with the categorized classes of molecules. Is that all I need to say? Hydrocarbon. Yeah. Now, true, this is an organometallic, so you could imagine that it could also react with any of these. Okay? But the utility of the Gilman typically is to make a hydrocarbon. And if you wanted to make an alcohol, go ahead and use either the Grignard reagent or the organolithium. One more to label, and then we're done. Okay, let me zoom out. And down here is the roadmap for the Gilman reagent.